Welcome to your first Unit 10 lesson. So Unit 10 will talk about the factors that affect the rate of a reaction. We'll go through them one by one, so we'll just see a couple in this lesson, but we'll see more in the next lessons. So first of all, 10.1 talks about the nature of the reactant. So what do we mean by that? We need either the phase, so phase of the reactants, solid, liquid, gas. So for a solid, because it has less energy, this will tend to react more slowly. A gas has more energy, higher temperature, right? So in the case of a gas, because it has more energy, it will react faster. So the nature of the reactant will affect the speed or the rate of the reaction. Now, what else? The number and strength of the bonds. If I have a single bond, it's much easier to break than a double or a triple bond. A triple bond requires, again, more energy to break it, which means it'll make for a slower reaction. If you have a bunch of molecules that all have single bonds, they will react much more quickly. So, as a summary, less bonds is better, faster, and something that's warmer is also better or faster. Now, in the case of a mixture, it works a little bit differently. So in a mixture, we have two types of mixtures, right? We have homogeneous and we have heterogeneous. They don't mix. Now, in the case of a homogeneous mixture, it'll go pretty fast because these particles can basically collide together easily. Their odds are higher of colliding together because they have particles of other kinds surrounding them. In the case of a heterogeneous mixture, well, because the particles are separated, they're not as much in contact together, which means the rate of the reaction will be slower. The only place where they can react is at what we call the interface, where they're in contact with each other. So this particle can react with this one, maybe, and this one with this one, but the others, such as this one, and this one, have to wait their turn, which slows down the whole process. It slows down the reaction. So in the case of a homogeneous, the reaction rate will be higher. In the case of a heterogeneous, the reaction rate will be slower for the reasons I just explained. Also, depending on the type of mixture, the closer the particles are, the greater the forces of attraction. So again, if we go back to the solid versus the gas, the solids are less reactive because the particles are closer together. So you have a harder time breaking those interactions. And why are there interactions? Because the temperature, again, is lower. So because the particles are moving less, it keeps them closer together. They have forces of attraction keeping them together, and that makes it more difficult for solids to react. As opposed to gases, again, they're further apart. They have more energy. They already broke those interactions. They turned into a gas a while ago. So because they have more energy and they're not linked together through attractions, it makes it easier for them to react. So, trick question. In what form does a substance react the fastest? Now, probably you would tend to say that it's in the gas form. Actually, we already discussed that there's something even more energetic than that. So you could be tempted to say plasma, but actually there's something better than that. And it's in the ionic form. Because ions are unstable. They carry a charge, right? So they're really eager to react. So whether I have a positive ion or a negative ion, it doesn't matter because it has a charge. It wants to react badly to become more stable. So these will react faster than a solid, a liquid, or a gas that are neutral. So if I had to rank things from low to high rate, I'd have solids have a lower rate, liquids, then gas, then plasma or ions. Let's put ions in general, because that includes solutions, and ions would have the highest rate of reaction. If we talk about bonds, we'll have triple, we'll have double in the middle, and single bonds would have the highest rate of reaction because they're easier to break. Now, some molecules are very big and they have a lot of bonds. So some are strong, some are weaker, depending if they're single or double or triple. So the triple, we said, will take more energy to break them. And that translates into a higher activation energy. So if I have a graph and I have my reactants here, and I have, let's say, a bunch of substances with triple bonds, well, my activation energy will be super large. If I have instead, so this would be for triple. If I have instead single bonds, well, my single bonds are easier to break, so they don't require as much energy to break those molecules. The reaction doesn't require as much energy. So the energy that has to be supplied being not as large, my activated complex is much lower, and at the same time my activation energy is also smaller. So in blue I'd have the single bonds. So the smaller the energy required, the lower the activation energy, and also the lower the activated complex. So this here would be a faster reaction. And for the other one, this would be a slower reaction, much more difficult to go over the hump. The second factor we're going to see right now is the surface area. Let me ask you a question first. I have these zucchinis and I have these zucchinis. Which ones do you think are going to cook faster? If you throw these into a pan versus these, I suppose most of you would say instinctively these. The question is why? Well, the reason is they have a higher surface area. Here, the heat can only touch the outside, so it'll take a while before the heat can actually go towards the middle of the zucchini and cook it. Here, the slices are so thin, the heat from the pan, given by the oil probably, will be able to touch and reach the whole slice, so your slices are going to cook much faster. It's the same thing in the second example. If these are cubes of wood, which one would burn faster? Well, here the flames are going to be able to touch here and on the side here, and that's it. But the flames won't be able to reach the middle. In this case, the flames can go in between because the cube is cut in smaller pieces, as well as touch these surfaces over here. So it's not as bad. In this case, well, the flames can go in between everywhere over here, as well as touch all these surfaces on top, on the sides, etc., etc. So here the fire can really penetrate the block of wood, and this would burn much faster. Again, why? Because it has a greater surface area. So the smaller the particles, basically, as you can observe here, this is a smaller particle than this over here. So the smaller the particles, we would say smaller particles equals higher surface area, which means, let's make this a double arrow to not mix ourselves up, which means a higher rate of reaction, a higher speed. So smaller particles means higher surface area, and that means a higher rate of reaction. Which leads me to the next question. Why is it a bad idea to light up a cigarette inside a grain silo or around sawdust? In a grain silo, you have a lot of dust from the grain, and it's in suspension in the air. So it's the same as being in the middle of a pile of sawdust. So why is it bad to light up a cigarette? Well, again, because the particles here are so small that they're very reactive. It's easy if you light up your cigarette with a match or with a lighter, it's easy to make them catch on fire. And actually, this is going to be such a quick fire that it would actually be an explosion, because an explosion is a very, 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 very fast combustion. So to light up a cigarette in this situation would actually cause an explosion. So here we go. To increase the surface area of the reactivity of a solid, we tend to dissolve it. Why? Because if we dissolve it, we create small particles like this rather than keeping them whole like this. If you think of a grain of something, maybe let's say salt, a grain of salt would look like this, but once you Once you put it in water, well, your grain will be broken apart by the particles of water, and what you'll end up with is all these. So it increases their surface area, and it makes for a faster reaction. In the case of a mixture, what do? We stir it. So that creates a more even mixture. Whether we have a homogeneous or heterogeneous mixture, we can stir it and kind of force it to become momentarily homogeneous, either more homogeneous or just homogeneous if we did start with a heterogeneous mixture. So to stir and mix will help, and to cut down a solid into smaller pieces will also help, or to dissolve it would do the same job. So these are the three ways that we can increase the surface area of a solid and therefore help the reaction occur faster. So that's it for now. Let's take a break, and I'll see you for 10.3.